Hi, good morning, everybody. So if you are in this room, also Laura, you probably have to, yeah, there we go. So hopefully this works now, that you don't mute your laptops in here. Welcome, everybody. Welcome back. Welcome to NKU. We haven't been here for a while with the KAS meeting. The last one was here 2018, 2017. It was a snowy day. It was icy. My students, when I was in Moorhead, they were trapped there because they had an ice storm in Moorhead. And coming up from Lexington was not a fun drive either. So this was hopefully a much more enjoyable drive coming here. So thank you, everybody, for coming here. I will give it over to our chair for this meeting.
Right.
Yes,
Sounds good.
Take it away.
All right. Just real quick, as far as logistics go, of course, we've got snacks over there again. The coolers with drinks are up here in the front and coffee over there to the side. Restrooms are kind of out the door and down the hallway past the elevators all the way at the end of the hall if you need to use those. And I think that's probably all we need as far as logistics. I think most people have put their posters up outside in the hallway there, so I think we should be good to go there. So welcome to day 2 of the KAS meeting. Hope everyone enjoyed day 1. It was really a treat for me to see the observatory filled with researchers again, and your all's presentations were excellent. It's my privilege today to introduce our keynote speaker, Dr. Laura Lopez. Laura Lopez is a professor of astronomy at the Ohio State University. Previously, she was a NASA Hubble Fellow at the Harvard-Smithsonian Center for Astrophysics and a NASA Einstein Fellow and Pappalardo Fellow in Physics at the Massachusetts at MIT. She completed her PhD in Astronomy and Astrophysics at the University of California, Santa Cruz, and her bachelor's degree in physics at MIT. And she is originally from Barrington, Illinois. You'll have roughly 50 minutes or so.
Okay.
I'll give you kind of a 5-minute signal towards the end, but otherwise,
sounds good.
Yeah, let's welcome our speaker.
Thank you. Thank you all. I'm very happy to be here at the Kentucky Area Astronomical Society. I'm glad you included Ohio as part of the area. And I'm going to talk today about stellar feedbacks and outflows in nearby galaxies. So we're going to do 3 different scales in this talk. We're going to do individual star-forming regions in the Milky Way and the local group. Then we're going to turn to nearby galaxies out to 30 megaparsecs. And then finally, we'll do feedback and its ability to launch gas into outflows of nearby galaxies. And I want to start by acknowledging my group who largely led this work. So I have 7 outstanding graduate students at Ohio State who are unknown to them, shown here. So a lot of the work that I'm presenting was led by them. And then I have many outstanding collaborators that also contributed, including Stephen Lenker, who is now a graduate student at Kentucky and is right there and speaking in a couple talks. And so for the second part of this talks, I will include work from the FANGS team. And I think we'll hear about more in the next session about FANGS as well. So I like to begin talks with conclusions because I know I have your maximum attention right now. And so the conclusions for this talk are that high resolution multi-wavelength data enables a complete inventory of the multi-phase ISM and of outflows. And, there's lots of different phases of the ISM, and I'm going to argue that the most poorly constrained is the hot phase. And so that's going to be the emphasis of this talk, is the interplay between the hot phase and the other components. And like I said, we're going to go through 3 different scales. We're going to start with star-forming regions in the Milky Way and the local group, which offer the most resolved view of what's happening. And we'll talk about where different modes of feedback are going, but specifically focusing on stellar wind feedback and how wind feedback is lost from regions through a variety of mechanisms, including turbulent mixing, conduction, and leakage. We'll also talk about how early pre-supernova feedback is able to accelerate cosmic rays and how we've detected gamma rays from young star-forming regions where no supernovae have occurred. Then we'll go up in scale to nearby galaxies and talk about the FANGS survey. And my role in FANGS has been to add the X-ray component to look at the hot gas. And I'll talk about how we have new Chandra and XMM programs to observe nearby galaxies and get the first subgalactic views of hot gas outside of the local group. And then third, we'll talk about galactic outflows. And again, focusing on the hot phase and how it can entrain the cooler phases. We see that the hot gas extends up greater than 10 kiloparsecs away from disks. We produce profiles of the hot phase, and we find that you need mass loading of cooler gas, and you need a non-spherical geometry for the outflow to account for the profiles that we observe. We've done this for a handful of galaxies, and now we're extending it to a larger sample of galaxies, particularly dwarf galaxies, to see how outflow properties change as a function of, for example, stellar mass and star formation rate. Okay, so that's what's in store. Let's first talk about the importance of stellar feedback. Really, feedback is really important on small scales of individual stars up to the large scales of galaxies and the circumgalactic medium. I'm just going to give you two examples of how feedback is important. So the first is that stellar feedback is necessary to produce realistic galaxies and simulations. And this was first realized in the 1970s, that if you try to produce the Milky Way without stellar feedback, you get a picture like the one on the left, which looks nothing like the Milky Way. So all of your baryonic material would accrete to the center of your dark matter potential well, and you would end up with a bulge that's about 10 times too big in mass and has way too many stars compared to what we observe. However, if you incorporate stellar feedback into simulations, then you remove material from that bulge and you end up with a more realistic size bulge and the extended disk structure like we associate and the spiral arms as well. So stellar feedback is necessary to produce galaxies like disk galaxies. It's also necessary to produce realistic dwarf galaxies, for example. Another place where stellar feedback is important is in terms of getting gas out of disks into the circumgalactic medium. So the poster child for this is M82, which is a nearby starbursting galaxy. This is a 3-color image that shows you the hot gas in blue, the dust in red, and the warm gas in green. So the warm gas is tracing the disk, and you can see that the hot gas is entraining the warm gas and the dust and getting it out to kiloparsec scales. And if you zoom into a part of the outflow, you can see that there's a lot of interesting structures there and these really cool arc shapes. And we're very perplexed at how you get these kinds of structures. But we see that lots of the material at the disk is getting expelled. We think driven by supernovae and entraining all of the different phases of the ISM.
So the bow shocks, are they coming from the interaction basically between the gas that is between M81 and M82?
Oh, so that's, yeah, so M81 and M82 are interacting. That is probably what triggered the starburst.
Mm-hmm.
But in general, these are the outflows driven by the starburst in M82. Yeah. So it is interesting to zoom out and see what the M81, M82 interaction is doing as well. Yeah. Okay, so in general, when we talk about stellar feedback, it's important to recognize that there are many modes of feedback that contribute depending on the age of the stars that you're thinking about or the age of the region that you're considering. And so this is a nice schematic of the stellar life cycle and molecular cloud life cycle from Schinnerer and Leroy 2024, a very wonderful review. And so this shows you the life cycle of a molecular cloud. And up above, I wrote which stellar feedback mechanisms contribute depending on what phase in the evolution you are. So your molecular cloud collapses and makes stars. When the stars are just being born, protostellar outflows are the dominant stellar feedback mechanism. They deposit momentum to their surroundings. Once the stars enter the main sequence, you have pre-supernova feedback, which is a lot of different mechanisms, including radiation, stellar winds, and photoionization heating. This pre-supernova feedback acts to disrupt the molecular cloud. So even before the supernovae happen, you end up with a molecular gas getting disrupted around the new stars. And then finally, 4 mega years and later, after the stars are born, you have supernovae occurring, and this ultimately destroys the molecular cloud, and you have not only supernova feedback, but you also have cosmic rays accelerated by the supernova shocks. And depending on which feedback mechanism and which age you're looking at for a particular star cluster, you're going to need to use different wavelength observations to probe what's happening. And so this is a sort of representation of what kind of telescopes you could use for the different parts of the evolution, where if you're looking at the molecular gas, you really want to use a telescope like ALMA, whereas when the stars are born, if you want to see the stars themselves, you want to use HST. If you want to look at the photoionized gas, MUSE is very powerful. And as you get to shock-heated gas from stellar winds and supernovae, then you need things like Chandra and XMM to view the hot gas. And then finally, cosmic rays, Fermi gamma ray observations are very important to constrain what's happening with cosmic ray feedback. Okay, so that's why it's important to use a variety of telescopes to view these systems to get a full inventory of what's happening. If, for example, only one is used, then you might only get part of the picture and not the complete view of what's happening in the ISM. All right, so in general, we have several motivations and questions that we want to consider. In general, a key idea here is that stellar feedback is one of the biggest uncertainties in star and galaxy formation models today. And so we want to try to make it less uncertain. And so to do that, we want to address a few different questions and sort of topical areas. So one is to get a complete inventory of the ISM. And to answer that, we need to know what is the baryon and energy budget of the different phases, how are they related to one another, and how does it change depending on, for example, the age of the stars and the molecular clouds, for example. 2 is the impact of the feedback. How does feedback couple to surroundings from small to large scale? So where does the feedback go? Where does that energy? We have lots of energy momentum, but yeah, where does it go? And part 3 is linking it to the environment. How do feedback properties depend on, for example, the properties of the host galaxy, like the stellar mass, whether you have a dwarf galaxy or a Milky Way or something bigger? And then how does it depend on local environments? For example, the centers of galaxies versus the arms of disk galaxies versus inter-arm regions. These are very different environments, and they can change the properties of the feedback and the gas pretty dramatically. So in terms of my approach and my group's approach, we try to use multi-wavelength data in the Milky Way and nearby galaxies because this is where stellar feedback can be best resolved. By resolved, I mean at sub-kiloparsec or parsec scales. And in this talk, I'm going to focus on the interplay of hot gas and its relationship to the other phases. So I'm going to use a lot of X-ray observations, but we're going to see a lot of multi-wavelength comparisons to understand where that stellar wind and supernova energy is going. All right, so as I said, we're going to do 3 different scales. We're going to start with local group star forming regions. And so a good place to look here is in the Milky Way itself, but also to look, for example, at the Magellanic Clouds and to focus on H2 regions. So these are some H2 regions in the Milky Way observed by Lisa Townsley with the Chandra X-ray Observatory. And from these 3-color images where you have the X-rays in blue, you can see that the hot gas really pervades the low density cavities of these young star forming regions. And so this hot gas is produced from stellar winds and supernovae that have shock heated the gas. And that gas pretty quickly ends up filling the entire low density cavity and even escaping out of the holes of the warm gas. So we can see this readily when we observe these nearby star forming regions, and I wanted to turn to 2 regions in particular for this talk. So the first is 30 Doradus, so otherwise known as the tarantula. This is a starbursting region in the Large Magellanic Cloud that is really beautiful. And this shows you an image of the region observed for 2 megaseconds with Chandra in a program called T-Rex, which is the tarantula revealed in X-rays. I know, it's well named. And so the Chandra data is in blue, and the central star cluster is there in the middle. That's R136. This is a really amazing superstar cluster. It has 2,400 OB stars. It has 4 of the highest mass stars ever detected or discovered, above 250 times the mass of the sun. It's really a great region to look at stellar feedback. And so 30 Dor, it's powered by R136, but it has sort of 5 different cavities that are filled with X-rays that are produced probably by multiple generations of star formation, not just R136, which is 2 mega years old. And you can see that the X-rays in blue really fill those cavities. So a question that my group had was, these X-rays, where is that energy going? And in R136, which is 2 mega years old, the supernovae haven't happened yet. So we just have stellar wind energy that is shock heating the gas. And we asked the question, where does that wind energy go? And to answer this question, again, you need a multi-wavelength perspective. So you do need the X-ray observations, but you also need to look at the dust and the warm gas to see where that energy is going. So this is work led by OSU PhD student Jennifer Rodriguez. And so this paper was published recently. And one of the things that Jennifer did was compare Chandra X-ray data from the 2 megasecond program to HST H-alpha data. And she did surface brightness profiles of the different cavities in 30 Doradus, looking at how the Chandra X-rays relate to the warm gas, the HST H-alpha. And what she found was that in general, the X-rays peak interior to the warm gas, the H-alpha. We see an X-ray decline at the H-alpha shells. So you can see the black lines peak before the green lines here. And so this is a signature of cooling and turbulent mixing that happens at the hot-cold interface, where the blue is touching the green in the picture. And in general, when we make these kinds of interpretations, it's really important to compare to simulations. So this is something I'm going to do a few times in my talk, is not only show the data, but also show our predictions from simulations and how they compare, because then you can actually reveal more of the physics that's happening. And so Lachlan Lancaster, a postdoc at the Flatiron Institute, did simulations of a star cluster like R136 and made mock images of the X-ray and the H-alpha, and then produced the exact same profiles like what Jennifer did and compared them to see what the differences were. And that would inform us about what is happening, what physics is contributing. And so these profiles are the ones that Lachlan produced with his simulations, and they're in Jennifer's paper. And so these are from 3D simulations of feedback-driven bubbles that include turbulent mixing, but do not include other kinds of cooling. And what he found was that the simulated profiles agree, except they have less interior X-rays. So you see that dip of the black line there. And we also see that there are no hard X-rays. So the peak is only in the soft X-rays, whereas the medium and hard X-rays are basically non-existent, the flat lines there. And so this is where the physics comes in. We say what produces interior X-rays and what produces sort of broadband X-ray emission. And that's where we end up saying we need thermal conduction and we need mass loading. That is mixing of the warm gas with the hot gas in order to produce the profiles that we see. So it's awesome that he was able to show that the X-rays peak interior to the H-alpha, so there is confinement of the hot gas, but you do need other physics in order to produce the profiles that Jennifer got from the Chandra and the HST data. Okay, so that was 30 Dor. The other fun place, there are many fun places to look in the local group, but another is N79. So this is a less publicized proto-superstar cluster that's on the other side of the LMC. So this shows you an H-alpha map of the LMC. 30 Dor is located on the left side, N79 is on the right. So they're both at the leading sort of arms of the LMC. And we think because of the way that the LMC is moving, that is triggering starbursts in both of those locations. N79 has accelerating star formation rates in the last half megayear. And so some of the papers like Oschendorf and Nyack say that this is a proto-30 Dor that's just in the process of turning on. And then there's been some beautiful JWST observations of the region where you can sort of see it shining brightly, and it's very embedded, the proto-superstar cluster. All right, so we targeted N79 with Chandra to get a map of the hot gas. We were interested to see how does stellar wind energy contribute and get lost at these very early stages in star formation. And so these are the different bands of the Chandra X-ray data with YSOs discovered by JWST, that is young stellar objects, stars that are just turning on. And you see 5 different YSOs in the region, and the X-rays actually coincide with one of those in particular, but the X-rays are diffuse. So they are 10 arc seconds in size. The PSF of Chandra is half an arc second, so this is resolved. And they peak sort of offset from the primary YSOs, but coincident with some of them. And this demonstrates to us that stellar winds do produce shock-heated gas, even at the earliest stages, like before they've even entered the main sequence. Stellar winds do produce hot gas that sort of contribute to X-ray emission that we're able to detect. The other interesting comparison that we can make is, again, to multi-wavelength data. So this region, N79, has been observed with HST and with ALMA. And so this shows you the 13CO map, and you can compare the X-rays to it, also the H-alpha. And what we find is that it's really awesome that the X-rays kind of fill all of the low density regions that we see in the ALMA map. And we can see that the X-rays are actually escaping from the holes in the dense gas. So this is really interesting because it means that the wind energy is already being lost from this young region via physical leakage from the star forming region. But we think that all of the mechanisms that we talk about for 30 Dor also contribute. So turbulent mixing, radiative cooling, etc. And so it's just very interesting to, again, consider multiple different regions, see what's happening, and see how it changes as a function of age. So another area of work we've done related to individual star forming regions is to see how much pre-supernova feedback can accelerate cosmic rays. So often cosmic ray feedback is a really hot topic right now in terms of galaxy formation. And often, in fire simulations, if you know Phil Hopkins' work, they only consider cosmic rays from supernovae. So we were interested in the question of, can they come from younger star forming regions where supernovae have not occurred? And so this is work led by PhD student Parmita Pandey, and she has done analysis of star clusters in the Milky Way that are younger than 3 megayears, so supernovae have not occurred yet. And we did a sample of regions, but the one we focused on first was RCW 38. This is a region that is half a megayear old. Supernovae have definitely not occurred. And she detected it with a 22 sigma detection with Fermi in the GeV range. And so this is a map showing you the Fermi gamma ray emission in blue with the Spitzer 3.6 micron in red that shows you the star forming region, and the Chandra X-ray rays in green, which shows you the individual stars. And doing an inventory of the gamma ray emission and the expected wind energy that we get from that star cluster, she found that 40% of the wind energy must go into cosmic rays to account for the gamma ray detection. So this is a very significant piece of evidence that shows that stellar winds can contribute, we estimate, something like 10% of the cosmic ray energy budget in the Milky Way. In follow-up work with Stephen Lenker and Parmita, we looked at even younger regions that have what are called explosive dispersal outflows, EDOs. So these are regions where you have young star clusters where the stars are actually kind of colliding dynamically, and that is actually producing these outflows like protostar outflows, but with a little bit different dynamics. And you can produce these even when you have no main sequence stars, so even before the main sequence. And DR21 is one of these regions that has explosive dispersal outflows. Parmita and Stephen found that it was a 40 sigma detection with Fermi, and that a significant fraction of the energy from the outflows can go into cosmic rays. We think that based on the rates of explosive dispersive outflows, maybe 1% of the cosmic ray energy budget in the Milky Way goes from EDOs, but still it's very useful to know that this could be another source of cosmic rays. Okay, so that was my take on the first scale of individual star forming regions. Just to mention what will be exciting in the future, one of the things that will be exciting is local volume mapper. So they are completing LVM as part of SDSS-5, which is doing an optical IFU survey of many star-forming regions, including the galactic plane, as well as the Magellanic Clouds. And using the IFU data, you can probe feedback, stellar feedback, as well as chemical enrichment on sort of sub-parsec scales for the Milky Way, as well as maybe 10 parsec scales in the Magellanic Clouds. And you can do a sort of similar inventory, but for many regions, looking at how the feedback changes across these different environments and sources. All right, so that was scale, or part one. Part two is going to larger scales and looking at nearby galaxies and feedback there. And so for this part of the talk, I'm going to emphasize work from the FANGS collaboration. And I think we'll get to hear more about FANGS in the next session. So FANGS is physics at high angular resolution of nearby galaxies. And so this is a survey of 74 plus star forming baseline galaxies that are 3 to 30 megaparsecs away. And it was initially started as an ALMA survey of nearby galaxies. So the image on the right, and Jayi did a lot of important work on cloud structure and cloud environment of molecular gas with the FANGS ALMA data. But it has since been expanded across all wave bands to do a full inventory of the ISM, including FANGS JWST to look at dust properties, FANGS HST to look at stellar populations, FANGS MUSE to look at ionized gas, and then FANGS Chandra, which is the latest part of the program to look at the X-ray binary population, the AGN, and the hot ISM. Okay, so just to show the beauty of this data, these are the images from the first 19 galaxies observed with FANGS JWST. So these are really beautiful, and there's really a ton of information to gain from it about the stars and the dust. Just to show you what kind of sample we're dealing with, across these 19 galaxies, we have 100,000 star clusters, 40,000 H2 regions, 2,200 supernova remnants. So this is to say that there's a lot of way to slice and dice this data depending on your individual interests. And all of this data is publicly available, so you can go play with it and do whatever your heart's desire is with it. There's really a lot here. Okay. So as a consequence of it being so beautiful and detailed, there's a lot you can do across the whole sample of galaxies, but there's also a lot to do with individual sources. So I'm first going to show you some results from individual sources, and then I'll show you some results from the larger sample. So just to demonstrate what we can do with individual sources, NGC 628 is one of those that's always one of the first ones that we look at. And so these show you on the left, ALMA and MUSE data that has 50 parsec resolution. And you can see that the cold gas, the ALMA data, is spatially offset from the warm gas in the MUSE data. And so this tells us about how the sort of molecular cloud and star formation process has different time scales and can constrain those time scales. If we look at the same galaxy with JWST, which is the image on the right from Liz Watkins, then we get 5 parsec resolution, so even better data. And this is really some of the most beautiful data ever. But in the Watkins paper, she identifies 1,700 bubbles, and each of these cyan circles represents bubbles that she visually identified in the data and then went back and looked at the stellar populations associated with them, the kinematics, things like that, and confirmed that they were bubbles and found 1,700 just in this one galaxy. So like there's a lot of statistical work that can even be done just in individual sources, and we can do this across 74 plus galaxies as well. All right, so as I said, this talk is going to focus on the hot ISM. And this is really my slide to acknowledge or say that our understanding of the hot ISM in nearby galaxies outside the local group is extremely limited. And I think this is because most of the people who do X-ray work focus on X-ray binaries, and then they never bother to take the point sources out and look at the hot gas. And so this shows you 2 of the works that have historically been done on the hot ISM. First for M83 by Tyler in 2004. And you can see that the hot gas in X-rays traces the spiral structure of M83. So once you remove the bright point sources, then you can see this diffuse hot gas and how it does trace the star formation that you get with the H-alpha and the mid-infrared. And then another work done by Mineo et al. In 2012 showed that when integrated over galaxies, the hot gas luminosity on the y-axis spatially correlates with the star formation rate on the x-axis. And so this is literally the only work that has been done looking at galactic scales and then on subgalactic scales for the hot ISM. There's been a few others that I haven't highlighted. Zhang et al. 2025 did M51, but really people haven't done it at a statistical level for many galaxies yet. So this is what motivated us to do FANG's Chandra. So we have all of these beautiful multi-wavelength data sets from the FANG's collaboration, and we said, all right, the hot gas is missing. And so with that in mind, in 2023, we did 2 different proposals that covered what are called the first 19 galaxies. These are the first targets of the FANG's collaboration, just as shown in the FANG's JWST images. We got 1 megasecond led by Brett Lamer at Arkansas and me. And then in 2024, we did a Chandra Legacy program for 2.9 megaseconds to cover all 74 of the FANG's galaxies with Chandra to look at the X-ray binaries, the hot gas, and the AGN down to uniform luminosity, X-ray luminosity. This was led by Smita Mathur, Brett, and I, co-PIs. And so just for reference, in general, when you look at X-ray observations of galaxies, you're going to have contribution from AGN at the center if they're there. And then otherwise, across the galaxy, half of the emission will be from X-ray binaries. So these are binary sources that have a neutron star or black hole. Their accretion disks are X-ray bright. And the other half of the emission will be from the diffuse hot gas. And so this shows you a simulated spectrum from Kristen Garofoli that shows you how the X-ray spectrum looks for the hot gas, which dominates the soft X-rays, and the X-ray binary population, which dominates the hard X-rays. And then on the right, I show you images from a particular galaxy, NGC 4321, to give an example of what the contribution is like for X-ray binaries and diffuse hot gas. So in the left image, you have the H alpha and the X-ray binaries. These are individual point sources that dominate. If you just look at the image, you can identify them right away. And again, this is why a lot of this data was initially taken in the archive, was to look at the population of X-ray binaries. Nobody bothered to just remove them and look at the diffuse hot gas. So if you just remove them, like literally subtract them out of the image, then you can produce the hot ISM of the galaxies, and you can see the sort of spiral structure like what we have in the H alpha in the left image. Okay. So that was our motivation, and we've started to get this data, and we're beginning to put it all together. So I want to show you some early results from the Fangs-Chandra survey. The first is the catalog paper, which is being led by Brett. And so this is a paper that hasn't come out yet, is likely to be submitted over the summer. So these are exciting, hot off the presses results that may change because we're still getting feedback from co-authors. But in general, what you can see is that all galaxies have a lot of contribution from different kinds of sources. This shows you the 3 X-ray bands. So the soft X-rays are in red. If you see them, that means that it's the diffuse gas contributing hot gas. Whereas if you see green or blue, that's going to be more of the X-ray binary population or AGN at the centers of the galaxies. And so just to show some of the exciting results from this, I kind of had to pick one thing. And one thing I found really exciting is that of the first 19 galaxies, something like 9 of them have AGN. And previously, we only knew 2 of them had AGN. So this is a really interesting result that shows you the importance of getting complementary data sets and X-ray data sets. So just to highlight this point, so Brett in his catalog identified all of the point sources in our first 19 galaxies. And then he took the complementary FANGS data from MUSE and JWST to produce the JWST color diagram, which is in the bottom left, and then the BPT diagrams using the optical line ratios in the top. And based on the placement of the point sources at the centers of the galaxies, in terms of the JWST colors and in terms of the BPT diagrams, we think that 9 of the 19 have central AGN. And these would be low luminosity AGN that were not confirmed previously. But again, the multiwavelength data hints at these natures, but the X-ray data demonstrates that as well. The purple are the central AGNs, and you can see that in general, they're falling into the AGN part of these diagrams. All right, so the other part that we're doing with Fangs-Chandra is looking at individual sources. And the first paper that came out was for NGC 4254. This is led by postdoc, or actually now he's a professor, Eric Monson. And so this came out just a month or 2 ago. And this shows you the 3-color image with ALMA CO in red, MUSE H alpha in green, and Chandra soft X-rays, so the diffuse gas in blue. And what we see is that the hot gas fills the gaps between the spiral arms. So you have highlighted areas of low density, including places of star formation, but also including inter-arm regions between the spiral arms of the galaxies. And for those who are not X-ray astronomers, one thing that's nice about X-ray CCDs is that you get not only position information, but you do get spectral information for all of your photons. You get the energy of the photons. And so you can take individual regions of the galaxy and extract a spectrum to get the properties of the hot gas, like the temperature, the luminosity, and see how they're correlated with things like the star formation rate, or star formation history that we can evaluate using the multi-wavelength data. So Eric went and used the hexagonal regions that Kai is a big fan of for the FANGS data and extracted X-ray spectra. and then looked at how it's correlated with the different multi-wavelength tracers, showed how the X-ray hot gas temperature is related to star formation rate, for example, and found empirical relationships. So one example is the empirical relationship that I've given here between X-ray luminosity and H-alpha luminosity. And this is like mind-blowing to me, but there has never been a pure empirical relationship between H-alpha and X-ray luminosity produced for galaxies outside the local group. So this is really, really important work to be able to understand the relationship of the hot gas with the other ISM phases. Another example of an individual source, a favorite again of the FANGS collaboration, is NGC 628. And so this is work led by OSU PhD student Karina Barbosa, who is taking the Chandra data, which you can see in blue, versus the JWST 7.7 micron in red, and the H-alpha for HST in green. And so this was the galaxy where Liz Watkins found 1,700 bubbles. And so we were eager to see, do the X-rays, what is the relationship to the bubbles? And Karina found that the bubbles tend to be filled with hot gas. So the one that is studied frequently is right here. This is called the phantom void. This is deserving of its own papers. But it's a large cavity produced by stellar feedback, and it is one of the most X-ray bright regions in terms of the hot gas. But the other part that's really interesting is that not only are the feedback-driven bubbles X-ray bright, but the cavities of the interarm regions are X-ray bright. And so to make that point, I like to highlight this area right here. So this is, and this, these are in between the spiral arms of NGC 628. So the spiral arms you can see in green, there's one right here and one here, and the X-rays are filling in all of the basically low density cavities, even if they're in interarm regions. And so we're doing sort of a detailed analysis to understand the properties of these regions versus the other ones. And what we're finding is that the arm bubbles tend to be more X-ray bright than the interarm cavities, but we're still in the process of doing it. Did you have a question? Because you're circling things.
No, I'm just annotating it, but I realize that everybody can see it now.
Yes, thank you. Yep, very good. Cool. I appreciate it. Okay, so in terms of future, we're still in the process of getting all the FANGS Chandra data for the full FANGS sample. The other thing that we jumped on was actually doing this with XMM. So for those who do X-rays, you'll know that Chandra is losing its soft X-ray response. It's not being able to detect soft X-rays anymore. And so it's not actually able to probe the diffuse hot gas as well as it could. And so FANGS XMM tries to address that by targeting basically the rest of the first 19 galaxies, particularly those that were not observed by Chandra early in the mission. And so the ones that are not in green are ones that were observed by XMM previously, and the ones in green were those that we targeted in a XMM program this past cycle led by Brett. And we're in the process of getting this data, and we'll do a lot more detailed analysis focusing on the diffuse hot gas in the FANGS XMM program. All right, so that was part 2. Now we're on to part 3. So for this, we're interested in how the hot gas is able to help drive or entrain the cooler gas. In general, we have this idea that starburst-driven winds are driven by supernovae that shock heat gas and then entrain the dust, the cold and warm gases in the flow. Again, I'm showing the picture from M82, and there are a lot of open questions here about how the hot wind couples to the cooler clouds. How are the cool clouds able to get far out and survive the hot gas? And then how does the wind evolve, and how many metals does it carry to the CGM? And when talking about outflows, people generally cite the foundational work of Strickland and Heckman, which did great work looking at the hot outflows of galaxies, including M82 and other galaxies. In particular, they measured the thermalization efficiency, which is the relationship between the E dot hot and the star formation rate. They also looked at the outflow rate of the hot gas versus the star formation rate. And these are very important constraints, particularly for models, but it is worth noting that they only focused on the central few hundred parsecs of these galaxies. So about central 500 parsecs. They did not look beyond the starburst region of these galaxies, all of this stuff that you see. So the circle shows you where they looked, and outside the circle is where they did not look. And this is where the hot phase carries the energy in the metals. So it's worth looking at the larger scales than those central areas. So with that in mind, my group began looking at starburst-driven outflows, with M82 again being the poster child, the one that we start with. And so in a paper that I wrote in 2020, we looked at the Chandra archival data from M82 and looked not only at the central region, so region D is the one that Strickland and Heckman looked at, but looking at the outflows many kiloparsecs out. And what we did was we extracted a spectrum from each location, modeled the spectrum, and then looked at how the properties of the hot gas change as a function of position along the minor axis of the outflow. And so to do this, we model the spectrum. Here's a spectrum. You can see the emission lines from different heavy elements. You have to include lots of different components on thermal plasma, charge exchange, and non-thermal emission to model it accurately. And this is where I want to take a side note, which is that it's important to include charge exchange. So charge exchange is a process when ions capture electrons from neutral material. So wherever you have hot gas in contact with colder gas, you're going to get charge exchange. You have hot gas in contact with cold gas in outflows. And as a consequence, something like 25%, even up to 40% of the X-ray flux from outflows comes from charge exchange. So there's nice work done by different groups looking at the high resolution X-ray spectra or CCD X-ray spectra and seeing what the contribution of charge exchange is. So the pink shows you what is produced by charge exchange versus the orange, which is what's produced by just a thermal hot plasma. And again, they find that something like 25% on average of the hot gas, of the X-ray emission comes from charge exchange. And the main point here is that if you don't include charge exchange, then you're mismeasuring the hot gas properties and the metals that are in the hot wind. And so this was part of why we included it in our models, and it was not previously included when people modeled the wind, the hot gas. And so fortunately, Randall Smith, Adam Foster, and Nancy Brickhouse did a model of charge exchange in 2012, and we were able to use it. Unfortunately, people before us were not able to use that. And so just to contrast how big a difference it makes, I want to show the previous results and then our group's results. So there was a very similar analysis of M82 to mine by Rinaldi et al. In 2008, who analyzed XMM data of M82. You have the central region in the circle and then doing the different regions just like I did. And these were the plots of the oxygen abundance, the neon abundance, and the magnesium abundance as a function of distance from the starburst. So 0 is the starburst, and then you have kiloparsecs away. And you see that for all of these metals, the disk is supposed to be very low metallicity, and then the outflows are like 10 times the metallicity of the disk. This is very confusing because how do these outflows get to be so metal rich when the disk is not metal rich? And the reason is because they did not model charge exchange. They were not actually accounting for the lines that were produced by charge exchange. So they over predicted the amount of metals in the outflows. So if you do include charge exchange, then you get a lot less metals in the outflows and you end up with flat profiles. So we included charge exchange as well as thermal plasma plus non-thermal, and we get these profiles for the same metals that I just showed: oxygen, neon, magnesium, silicon, sulfur, iron. You can see that in general you have flat profiles that even kiloparsecs away from the disk are very similar, and silicon and sulfur peak at the disk, likely because you have a hotter component there, and enrichment from supernova ejecta. But overall, we see that the metallicity gradients are fairly flat. So in addition to looking at the metal content, we also produce profiles of the temperature and density. So these are the black lines showing you R equals 0 is the disk, and then looking south and north of the disk. And we see that compared to what is called like the canonical model of a starburst-driven wind by Chevalier and Clegg, where you just have a spherical wind that uniformly expands adiabatically, then you get the solid color lines there. And that fits fine in the central region where Strickland and Heckman did look, but it does not fit when you get about a kiloparsec out from the disk. So you need to look at these larger profiles, and then you see that you need to go beyond this spherical adiabatic expansion model. You need to do a non-spherical model, so that is make something that looks like this as it goes out. And then you also need mass loading. You need warm gas to get entrained with the hot gas. And so there were great models produced by Dustin Nguyen, who was a grad student at OSU working with Todd Thompson. And so he did these models looking at non-spherical expansion, looking at mass loading. So these are the orange and the blue lines, and then comparing them to our data, which is in the black lines. And you can see that once you have models that do non-spherical expansion and that do mass loading, mixing of warm gas with hot gas, then you can produce the profiles that we observed. So like I said, M82 was just our sort of starting case. We've done this for many other sources now. This was work led by Sebastian Lopez, another grad student at OSU with the same last name. And he did it for NGC 253, NGC 4945, led by Natalia Flores Barrera, who was an undergrad. So these were our starting sources, but now we're applying this analysis to 25 galaxies that have a range of star formation rate, as well as a range of stellar mass, to test how outflows vary as a function of distance from their disk, but also as a function of the properties of the galaxy. So as I said earlier in my talk, one thing that is very important to do is to compare to simulations. Like we already showed, Chevalier and Clegg, a spherical adiabatic model doesn't fit well, but now let's actually look at other simulations. So there's great galactic wind simulations by Drummond Fielding, and his group was able to produce mock images and profiles from his 3D MHD simulations of galactic winds. And what he did was he took his simulations and tried to match, all of the different properties that we have from our paper on M82, and it doesn't match. And it's pretty amazing how it doesn't match. And so this is work led by undergraduate Allison Lin from Columbia. And so they did these simulations where they have they have pictures of the temperature, density, the X-ray luminosity as a function of distance from the midplane. And then they tried to produce the same profiles that we observed. So the black is our M82 data, and then the other lines are the simulations, which no matter what they do, they produce an X-ray luminosity that's 100 times too dim. And so it raises the question, and it does not matter what resolution they use, energy injection rate, boundary conditions, none of those are able to produce the X-ray properties that we get. And so the question comes in, okay, and then what physics is missing? And it basically is all those standard, what about this kind of questions that we have in astrophysics, which is what about magnetic fields, cosmic rays, conduction, mass loading, turbulent mixing, all of those things. And, this is really important work showing that it's different, right? Because it means that there are things missing from our best simulations. Okay, so like I said, we're in the process of doing this analysis for a larger sample of galaxies. And in terms of future work, the thing we're most excited about is measuring the metallicity of the hot phase and comparing it to the metallicity of the warm phase of outflows in galaxies. And so in particular, John Chisholm in 2018 made this plot of metal loading as a function of stellar mass of galaxies, metal loading of the outflow as a function of stellar mass. And he found that the smaller galaxies, the dwarfy galaxies, have more metals in their winds in the warm phase compared to Milky Way-like galaxies. And so we want to answer the question, is the same true in the hot phase? So the galaxies that we've done so far are more Milky Way-like, or a little bit less, and we want to go down into the smaller mass range of dwarf galaxies and look at the metal loading there and see how it compares to the warm phase. So we're beginning to do this for the hot phase and compare it to the black points that John did in 2018. And then the red and the blue line are theoretical models that predict the mass loading for the warm phase. So again, this is part of our motivation in looking at galaxies that have different stellar masses, for example, see how the outflows change for dwarf galaxies versus Milky Way-like galaxies. The last thing I'll say is related for future is related to hot gas kinematics. So one observable that we've always been missing in the hot phase is the ability to measure the velocities of the gas. And so CRISM, which was launched in 2023, is now able to do this for the first time for extended objects like galactic winds. And this CRISM collaboration paper just came out in the last month, looking at the wind of M82, where you can see spectral lines from all the different hot gas elements, including the iron, and they see a broadened profile for the iron 25 that's consistent with a velocity of 600 kilometers per second. Once you have a velocity, then you can measure actual outflow rates and energetics, which we couldn't do before. We can measure how much mass gets out compared to the other phases. So these are really important constraints that we were lacking before. If you look at any outflow papers, they're always like, it's 1,000, let's just assume 1,000 kilometers per second. These are the first actual measurements to show it. So it's very important. M82 so far is the only starburst-driven outflow observed by CRISM. And so I think people are trying to propose to do more. And I think this is really exciting future work. All right, so I will put up my conclusions again. Thank you so much. I'm happy to be here and meet all of you.
Any questions for Laura?
Yeah, Laura, thank you for an excellent talk. You showed really also the importance of multi-wavelength observations. What about the UV? Have you looked at the Swift UVRT data? Because Swift did a survey something like 15, 20 years ago with all the nearby galaxies, something like 400. Is the spatial resolution not good enough for FANGs, or what is it?
It is good enough, and we should do it. And I have made maps, and I'm going to look at Jai and just say, like, yes, we totally should do it. So Hamid Hassani did the Astrosat data in the UV. So those are our comparison. But I think we could add the Swift UVOT.
Yeah, because the data exists, right?
It is there. It's totally. I've gone and for nearby galaxies, just making the map of the LMC, which never got published, but it's all there.
It's all there.
Beautiful.
Yes.
UV
correct.
data of the LMC.
I mean, I don't think any of these data have ever been published. I don't know if there was a
they haven't. There was a press release that did it, but it was never published.
It was never published. The same with M31.
Yes.
Right. There was never an M31 paper.
So this is again an example of like the data was used for some other kind of science and it was never applied in this way before. Right. And I think it's all there, so it's just a matter of putting it together. Yeah.
Thank you.
Yep.
So metals go into the halo, like the feedback is sort of flowing it into the halo. So that was, for a while at least, the way to get metals in there to cool down in Milky Way type galaxies that you have precipitation coming back down.
Yes, yeah.
So I noticed that the metallicity was now flat, not going up, so that makes that efficiency a lot lower.
Yeah.
Can you say anything about that, or is that?
Yeah, I haven't thought about this in the context of inflow, but I think it's a good question, because yeah, some of it will come back, and I'd be interested to know more about like what the best way is to constrain that. If I've thought about it like as a mutually, like if we can try to constrain, like because it's coming, would it come in like?
So the way that people looked at it was with the H1 beards, so you have the kinematics, and then there's basically stuff that isn't rotating as fast as the disk is rotating, and so that is stuff that they sort of attributed that. There were a lot of explanations for beards, but one of them was it's raining down back onto the disk.
Okay.
But of course they look at edge-on galaxies for this, and not these lovely face-ons. So is that I guess you could look at the H1 profiles as well.
Mm-hmm.
I noticed H1 is still coming for a lot of these.
Yes. Yeah. I think we're getting H1 data on all of these.
Yeah, Meerkat.
Yes. Yeah. So I think we can start to look at it.
But that would be an interesting thing to link the X-ray outflows to, like how well is it, because the whole thing is like, how do you feed a Milky Way type galaxy new gas, right? And so this is in the H1 community, that's been like an ongoing theme I'm talking to them on. But like nobody knows where the gas is coming from, so this would be a fantastic way to do it. But I think the metallicity, like actually being able to tell how much it's going and then making a prediction would be very useful. But I was wondering if you could say how much metals are actually ending up there.
Yeah, I don't think we have, we're trying to go out as far out as we can and look at these profiles. It requires a large signal in order to measure metallicity though. So I think we can do it for a few sources and try to go out as far as possible.
Should be exciting.
Yeah.
Any more questions for Laura? Jesse?
This is going to be a fairly open-ended question, but I'm curious about how your findings here and comparisons against simulations might inform or are informing like feedback models in like cosmological scale simulations for like impacts on large scale structure.
Ooh. So my impression, you can tell me if this is right or not, is that the ones that are like cosmological scale are still kind of tuning the feedback. And so they're still just trying to match things. Is that right? Yeah.
My knowledge is vague there as well.
Yeah,
so
okay.
Generally curious.
So I feel like, so a lot of it is still very hand wavy, and that's part of why feedback is so uncertain, is because we're kind of just we're not testing it yet. And so I think that's still to be done, is to actually try to test more with these simulations. Yeah.
Let's thank Laura again. We've got a 15-minute break. You can do posters, can do snacks. I did just send out an email with the link to the interview from last night. I haven't actually watched it yet to see who's a new